What is up, guys? It is Mr. Connolly here, obviously coming through you at your webcam. I wanted to attempt this, online learning together. So I want to make a quick video just to show you of what to expect with however long we are out for school. I do want to start posting more videos. That way it does look a little bit more, normal, and that it gives some life behind the camera rather than just giving you and typing out some directions for you to follow. All right, so what we were talking about before we were sent home, all right, for extended break, we were talking about Alfred Wegener, and remember you were saying how like Alfred Wegener was like this really not likable scientist in the scientific community. A lot of people didn't like his ideas, and do you guys remember why? Of course, you can't respond to me, it's through a webcam. All right, well, why was because he had a PhD in astronomy, he had a PhD in meteorology, which deals with like the weather and the atmosphere, and so he decided, right, he looked at the continents of South America and of Africa, and he's like, wow, like what are the odds that these look like they match up completely? Like they look like two linking puzzle pieces that fit just perfectly together. And there was no way in his mind that this could have been by coincidence, or the only way was that maybe someday or sometime in the past, all right, 250 million years ago, maybe all the continents were lined up together, and he called this Pangea. And do you remember how scientists reacted to his ideas? Of course you don't, because it's a webcam. You can't talk back to me. All right, awesome. People thought, you're crazy, Wegener. Like, you are so wrong. All right, you look dumb. You sound dumb. And they would hold these conferences together literally just to talk trash about him and say, hey, can you believe how crazy Alfred is being? Can you believe what Alfred is thinking about the continents? He thinks that the continents are moving, right? And to them, this was just such an absurd statement, such an absurd hypothesis that he really was not like accepted in the scientific community, especially in geo and geophysics, because they thought, Alfred, you deal with the stars, you deal with the weather, we can handle the continents, we can handle Earth's surface. You have no knowledge of this topic. You don't have a doctorate, you don't have a PhD in what we're dealing with here, so stick to what you know, and we'll stick to what we know, and you can keep your crazy ideals to themselves. All right. So we kept going further into his continental drift, and this is the hypothesis that the continents are slowly moving across Earth's surface. And one of the main reasons also why his ideas were rejected at the time was because when they asked him, okay, Alfred, like explain yourself, or like, give us the evidence, give us why you think so. He was like, I don't know, I have no idea. And they're like, well, because science, you can't just say you feel a certain way through emotion, right? You have to have evidence. You have to have factual data. You have to have analytical responses that can be backed up by evidence that you present to present your case. And because he could not have or describe the driving mechanism or the driving force that moves these continents over the surface of our planet, they said, Alfred, no. You're ridiculous. We do not believe you. There's no evidence, no hardcore proof. So because of that, Pangea was never a thing, and you can't persuade us to think that you're right. So over time, this really angered Alfred Wegener. All right, he said, "Okay, bet I just said that he's going to find that evidence, and he's going to prove to himself and to the rest of the scientific community that he actually is true." All right, so what he found was the first one was land fossils. B was land and surface fossils. There's another key argument or key piece of evidence that he found. And then he also looked at the global climate change throughout millions of years of history to explain that the only way you will find tropical fossils in Arctic regions is because at one point these Arctic regions today must have been somewhere along the equator where we know the climate is generally warmer. All right, so the first thing he found was fossils. And when he looked at these fossils, one fossil in particular was a Glossopteris fossil. All right, it was a fern-like fossil about 250 million years ago during the Permian period. Remember the Permian extinction. And when he found this Glossopteris, or he's finding Glossopteris on Africa, he's finding it in South America, Australia, India, and Antarctica. So for a second, let's just think with our general knowledge that we have. We know today Africa, South America, Australia, India, and Antarctica, which is a frozen tundra, all right, cannot house or hold these plants, right? These plants don't have legs, regardless of what your argument is. They don't have legs, all right? Some scientists said, well, the only reason you find those plants there is because when they were just a mere seed, maybe a wind current picked it up, blew it across the oceans, they said that, and then it just kind of landed on these different land masses that we call continents, and then they started to sprout and grow there. That was a really crazy idea, as much as they want to call Alfred Wegener crazy. These plants and these seeds are very, very heavy, and they're too large enough to be picked up by wind currents. Even if they weren't heavy, we're talking like thousands of miles across the surface of the ocean. It's impossible. You can't do it. So another piece of evidence he found was Mesosaur and Lystrosaurus fossils. These are small freshwater reptiles from the Permian as well, so we're in the Paleozoic still. And these are they're freshwater reptiles. So what happens when you place a freshwater organism into saltwater or seawater? I'll assume you said it dies. Yeah, it doesn't live. So they were also too small to swim over vast distances, such as from South America to Africa to Australia to India and Antarctica. So Alfred said, okay, what about now? Explain that. And they said, oh, well, clearly, Alfred, back then, there were bridges that connected all of the continents, and then they simply just walked across the ocean. No. So for some of you out there maybe looking at this saying like, yeah, that's what happened, change yourself. Nope. Think about what you're saying. I can't even see what you're saying, but I guarantee you, I know some of you, Ramsey, are thinking that this is true. It's not. All right? It's not true. All right? It's impossible. All right? And then they said, well, obviously that's the other reason why Glossopteris made its way across the ocean. These animals walked over the Glossopteris plants, seeds, stuck to their fur or their scales, and then when they walked across the bridges, because that's what was then, back in the day, there was bridges. If you ask me where the evidence is today, they'll just say it's sank to the bottom of the ocean. Okay, not really fair, but all right. They distributed the plants that way. So that makes sense as to why we found Glossopteris and Mesosaurs and Lystrosaurs. No, it doesn't make any sense. All right, the only way that you can find these plants, right, these seeds in all these different areas, I'm pointing to the screens if I can move it, all these different land masses, Africa, South America, Antarctica, India, Australia. The only way you're going to find Mesosaurs on South America and Africa, right, Lystrosaurus on India, Antarctica, Africa, is if at one point it was all connected. That's the only way that's possible. Right? The only way that these can connect is if it was one single landmass back 250 million years ago called Pangea. All right, so now Alfred's presenting his argument. He's saying this is why this happened. And they're still saying no land bridges. Nope, not possible. Okay, so let's look at land features. All right, if we match rock types and ancient mountain belts across vast distances across oceans, all right, we can also look at how they form a puzzle piece. All right, so just like South America and Africa, they form a puzzle piece together. If you put them together, they look like they match or they fit together like a puzzle, right? So do ancient mountain ranges. So for example, if you look at the mountain ranges of the Appalachian Mountains, all right, the Appalachian Mountains runs through Washington, D.C., like near that area along the East Coast, through New York. All right, the mountain ranges, I'm pointing to them right now, in our own backyard in Haskell, all right, these Appalachian Mountains, all right, the Rambo Mountains, okay? These Appalachian Mountains, if you look at where they cut off, all right, along the East Coast, up here near Maine, all right, if you connect this mountain range into those in the United Kingdom, in Ireland, in Norway, all right, if you look at the rock types, what do you think happens? Again, this is webcam. I can't ask you questions. If you connect the mountain range and the rock types, the Appalachian Mountains along the east coast of the U.S., and you continue this down into the United Kingdom to Dublin to Ireland, all right, parts of Norway and Germany, all right, the rocks are an exact match. All right. So think about if this was all connected at one point. Make sure, or not make sure, Pretend like this ocean was never here. All right, pretend like all the continents were fit together like a single puzzle piece. All right, this would make sense why these would connect together. All right, although this is now part of a different mountain, it's not called the Appalachian Mountains anymore. At one point, when this was all connected in Pangaea, all of these mountains were connected to form one major ancient basin mountain range. All right, but now that we have continental drift and the continents are being spread apart by this mid-ocean ridge right here, all right, as more ocean floor is being added and pushed to the left and to the right, all right, now we have an ocean dividing the continents, all right, and now we can see exactly what would have happened if continental drift made the continents go back into Pangaea, right? These mountain ranges would link up exactly, all right? You see the same thing. So here's the Appalachian Mountains right here, all right? This rock type connects all of these rock types, right? This is all at one point connected. I don't know why this is here. I don't know what's happening. Whatever's about to pop up, ignore it. Oh. Okay. Great. Fantastic. Thank you for interrupting. That's awesome. All right. Again, I don't know. All right. If you look at the, I don't know if you guys have ever been to, what's it called? The George Washington Bridge that connects parts of New Jersey near Hoboken into New York State. When you're going over that Washington Bridge, if you look to your left, you'll see a big cliff that looks very orange/red. It's due to the iron-rich rocks in that area. If you look at that rock type, and then you look at the rock types along the northeastern coast of Africa, the rock types are exactly the same. So during Pangaea, parts of New York City and New Jersey actually connected to portions of the northwestern portion of Africa. All right. So if you look at ever been hiking along that area, it's a very nice hike if you guys have ever done it. Those rock types match exactly the rock types that you'll find in northwestern Africa. So again, we're looking at similarities of what. It's not just a coincidence, right? It's not a coincidence that the ancient mountain ranges line up exactly, or that their rock types match up exactly. It's not a coincidence that the rock types in New Jersey/New York completely match up those of northwestern Africa. That's not a coincidence. The only way that could have happened is at one point it was together, a single landmass, and then it broke apart. Hi, Brody. He's going on a mission. Ignore him. All right. So, third piece of evidence. What? Brody. Okay. Ignore him. All right. Third piece. Climate change. All right. Another thing that happened is we're looking at fossil types again, but we're looking at how climate makes a huge impact on this now too. So if you look at climate change, all right, we're looking at Lycopsids. All right, it's a type of tropical plant that is found in modern day Arctic Ocean, North Pole, right near the Arctic Ocean. Brody, come here. Say hi. That's Brody. All right, anyway, so we're just talking about the Arctic Ocean. We're talking about climate change and Alfred Wegener. How do you feel about him? Okay. But when you look at the glacial deposits of similar ages of different rock types throughout, the different continents and different land masses, you can see that the only way that you can find a tropical plant fossil located in the northern region of the North Pole, near the Arctic Pole, the only way that's possible is if at one point that region was near the equator, right? Which would come again looking at continental drift. The only way that this can happen is if you have these tropical plants in frozen tundra regions today, is if at one point where that fossil is located, it wasn't actually in that location. It had to be somewhere along the equator, where we know that the climate is generally a lot hotter, a lot more humid, a lot more wetter for these types of plant fossils to survive in. So the only way you're going to find these tropical plant fossils in these regions in the north and south pole near the Arctic is if at one point that's not where that continent resided at. It had to be somewhere along the equator. All right, that's the only possible explanation for this type of continental drift and continental movement. All right, so Alfred Wegener eventually went on this expedition into